Hey everybody. All right, so I'm determined today to not go on and to mix in a whole lot of things. So having said all that, let's go ahead and begin with our second topic, which is to review inference for means, t-test, t-intervals for means. So let's just go right into it. Here is today's PowerPoint. So let's start it up from the beginning. And remember that when we're dealing with inference for means, we are moving from a z-curve to a t-curve. You'll recall this graphic. The black curve was a z-curve, and we had to modify the typical normal curve into something slightly different, sharing very much the same properties but a little different. A t-distribution comes when we have to move from standard deviation being sigma over square root of n. We don't know sigma. So we're going to have to go with the sample estimate for sigma, which is s over radical n. And with the variability that you get from, spread that you would get from sample to sample to sample, you have to make up for that variability by having less height in your curve and more area in the tails. These are all density curves. They all have an area of 1. So if you lose area in the height, it's got to pick up in the tails. The more degrees of freedom you have, the closer you get to a z-curve. So if you have 20 degrees of freedom, you're practically in a z-curve. And remember, all these curves are centered at 0, and you measure them in standard deviation units. So they're very similar to each other. They just are changed up a little bit from having to use s in place of sigma for your standard deviation. We have a t-table of values. There should be one for you to print out if you need it. It should be up on Canvas. If you can't seem to find it, just Google it and it'll show up. Remember, these are going to be the critical values for our confidence interval. The first row above the percentage that you want is going to be for a z-star. All the rest are t-star values based on degrees of freedom. And remember, this upper row is going to be for your right tail t probability for like a t-test. And you can pretty much estimate it by locating your degrees of freedom, finding what your t-value is, at least what it's between, and say it's between these two numbers, then p would be between 0.05 and 0.025, meaning that would probably be at a level that you could reject. So we have t-tables. All right, let's start out with a one sample t interval for means. If you're going to do a formal write-up, define the parameter. Mu is the true whatever. Assumptions, remember SRS and independent, and your 10% rule. The population is 10 times your sample size, at least 10 times your sample size. Those will be shared by both means and proportions. Your normality check, a little more complicated. Put it in a graph, box plot, or normal probability plot if given raw data. Modified box plot is best for outliers, and these intervals and t-tests are very sensitive to them, so you got to make sure you don't have one. If you do have one, that is a violation of normality. If you're told the population is normal, then the sampling distribution that you're in will also be normal. If you don't know those two things, n is greater than or equal to 30, if that's true, then the central limit theorem applies. That means that your normality of your standard distribution can be approximated. And I didn't list the final one that you could possibly choose from, but maybe if none of these things are available to you, then you can just assume it and maybe list it as a limitation at the end. Remember that t-procedures are robust to violations of normality or deviations from normality. So if you're graphing and you don't have a perfectly symmetric box plot, then you can probably accept it, because T procedures can be done when you're not perfectly normal. All right, name the interval, get your results from your calculator, report them, and then throw in your interpretation. We're 95% confident that the true average score on this particular test is between these two values. State any limitations. That should be pretty much it. Here is the formula, core sample estimate plus or minus margin of error. Here is your standard error, and here is a value related to the confidence level. You may need your t-table to look that up. You can do t-CDF to figure out, or I'm sorry, inverse t would be it. Inverse t can be a way to find your t-star value too. All right, a one sample t-test, again, define the parameter. Write out HO and HA. All right, HO is that mu equals some number. HA is that it's either greater than, less than, or not equal to that number. All of these are going to be the same assumptions that you would use for a one sample t interval. All right, so do the same checks. Call it a one sample t-test for means. Do it on your calculator. Once you have your results, state your t-value, your p-value, your alpha value. Don't forget degrees of freedom will be n minus 1. It should show up on your calculator results, but if it isn't, if you have 30 in your sample, then you have 29 degrees of freedom. Seems like there was something else I wanted to tell you. Definitely naming these things, again, will prevent you from having to use any kind of formulas for like confidence intervals or t-test statistics. You can do calculator speak once you've named it. You're pretty much good to go. And then provide a conclusion comparing p to alpha or base it on strength of evidence. List any limitations or violations. And FYI, here's your formula for a t-test statistic. Remember, it's your sample estimate minus what you've conjectured for HO divided by your standard error. Okay, so I'm moving along pretty rapidly. If I'm going too quickly, then go ahead and pause and write down if you're writing things. If you need more detail on this, you can always go back into the old formulas for t-test for means, and everything is posted there from before. You can take your time going over it. All right, two sample t interval for means, define the parameters mu1 and mu2. Assumptions, just kind of go plural, SRS and independent samples. Each population has to be at least 10 times the sample size. Same normality checks as a one sample, but again, you're checking for both samples. All right, call it a two sample t interval for means and produce it on your calculator. Okay, interpret it. We are 95% confident that the true difference in the population means for blah, blah, blah falls in the interval. Once you have your interval, look for and report 0, because that's mainly the reason that you're doing it, is to kind of look to see if there's a difference. Maybe they'll say, is there evidence that the difference between the two averages is 3? Then you would look for 3, but typically you look for 0. And if 0 occurs there may not be a difference in those two parameters at a 95% level. If it's missing, if everything is positive, like the low end and the high end, or both negative, positive or negative, 0 is missing, then you have evidence that the two may be different. Here is your formula. Remember that your two sample t interval is based on a difference. However, the order that you subtract here doesn't matter, because you're going to trap 0 or not, whether both of the values are negative or if both of the values are positive. All right, but again, plus or minus margin of error. Here's your standard error. All right, two sample t test for means, define the parameters, state HO and HA. The assumptions are the same as a confidence interval, so just use them as before. Call it a two-sample t-test for means. Do it on your calculator. State your t-value, your p-value, your alpha value. And remember, your degrees of freedom come out strange. They come out as decimals. They will be reported. If you are doing this somehow by hand, then you can do n minus 1, n1 minus 1, or n2 minus 1, whichever one is smaller. But just, you're going to see it in your calculator. Just grab it and write it down. Provide a conclusion comparing p to alpha, or base it on strength of evidence. List any limitations or violations. And here's your formula for your t-test statistic. Remember, HO is that mu1 equals mu2, or the difference is 0. So you're assuming this is 0, this piece of it. So it's really just this divided by your standard error. All right? So one thing that you may have noticed is that I left out matched pairs t-test. I felt like I ought to just do one of those from scratch with you, because just writing it out like this might be a little less revealing. But anyway, so that's what's coming up next. We'll do a matched pairs interval and test of significance. And hi, I'm back. Let's look at, let's see here, what do we have here? We'll get to that in a moment. I need to open, I believe it's this. Okay, this is up online if you want to download it for whatever reason, but this is a problem I totally made up. It's based on our current situation. We're going to use the following report card averages to determine if online learning hurts the performance of students in AP statistics. All values are report card averages, and we're going to use alpha of 0.05. All right. Now, the way that I'm going to know immediately if this is matched pairs is because they've given you this extra row here, which is just relating each ordered pair to an individual student. Student 1, student 2, student 3. So you're measuring each student twice. Once for in class, we'll call that like the 4th 6 weeks. And then once for online, we'll call that like the 6th 6 weeks. And we're going to just work off of the difference between these two rows, the in-class and the online. So really, although we've got two sets of data, we're really only interested in the difference, you know, 82 from 85, 95 from 93, 90 from 86. And so we're going to do a one sample t-test on that difference. So we're going to define the difference, mu of a difference right here, as the true average difference in report card grades between in-class learning and online learning, right? You need the little subscript D, or you can write DIFF, that's what AP typically does. So HO is that there's no difference between the two different ways of learning. HA, I deliberately picked greater than, because if online learning hurts the performance, then the difference should show up with a drop in the average, right? So greater than 0 would mean that online, I'm sorry, check that. Mu of a difference being greater than 0 means that your in class, if I subtract that, if I use that first in my subtraction, will be higher on average than my online, and so the differences should be positive, right? So I did note that it's in-class minus online, and if I'm seeing better averages for in-class, then the difference between in-class and online should be positive values, because online the averages should be smaller. Okay? So assumptions, they didn't say anything about SRS, so I'm going to assume it. Students are independently chosen, meaning that I don't have the student number 1 measured twice, or student number 5, or any of them. All right. I think we can safely say that your population is at least 10 times the sample size. This is 9. I have actually 109 of you. So 10 times 9 is 90. I'm good to go there. That condition is reasonable. All right, normality of your sampling distribution is verified graphically. This is where I'm going to have to go to the calculator and show you the setup and everything. So here's the calculator. I called this C, that was in class, and I put in all of those numbers, all 9 of them. And then O is for online. I put in all of those, making sure they're consistent. They're linked together the same way as in the table. And I do have all 9 of these. So make sure that you don't have 9 here and 8 here or 10 here. If you do that, then you'll get a dimension mismatch and you'll wonder what the heck just happened. So we don't really need these 2 sets of numbers for anything more than to just get a difference, right? So I called this third column the difference column, and that's going to take a formula which goes right here where I'm pointing. So we're going to say equals, that equals C minus O. So C subtract O. By the way, clearly you guys, if you need to pause the video while you play along with me, that's fine. If you just want to watch, then watch it to the end. All right, so hit enter. And we get the usual, is that a column reference? No, it's a variable reference because I named it. And just hit OK. And it's going to ask me again, since I set up 2 of them. So that's going to be a variable reference. And go ahead and tab to OK. And we don't, like I said, we don't need the values that we put in the C column or the O column. We are going to do a 1 sample t-test and t-interval on the differences. So we could just delete the 2 of these and just work with this. I wouldn't do it though. I believe these are all linked together. So I think the first thing we're going to do is to graph it and do that check for normality. So we'll go to a graph here, and we're going to go ahead and choose the difference. And then we're going to go ahead, don't type in anything here because we're not doing a scatter plot. Just go ahead, menu, and we want a histogram, not a histogram, a box plot. No outliers. Now you see it is skewed to the left. It's clearly skewed to the left. But it's not so badly skewed to the left that I'm going to worry about it. Really, the test will be robust to this sort of a departure from perfect normal. So I'm going with it. Even with a small sample size, I just don't have any outliers. And we can change that to a normal probability plot. And it will show a few bendies. Here's a bendy, here's a bendy. But in general, it's, it's making a start for the chair shape, but it's not so bad that I'm going to worry about it. So I'm going to go ahead and verify normality here. So normality of the sampling distribution is verified graphically. No outliers are present. So I'm good to go. Everything is confirmed. So this will be a results for a match pairs. I'll start out with a t-test for means, okay? There's the results. Let's just go ahead and run it so you can feel comfortable in it. So go home and go over to a calculator page so everything is linked. And this will be menu and 6 and 7. And we want a t-test. And we're going to do data. We're not doing summary statistics because we do not have them. All right, mu naught will be basically 0, right? No difference. We're going to do, our list will be the difference column. Leave your frequency on 1, and we do want greater than 0. Remember, that was our alternative. So we'll go ahead and right click here and choose greater than and hit OK. And here's all the values that I got, all right? Here's your T, P, degrees of freedom. And so back here, there they all are. Here's that same T value. Get to where I can check that off. All right, down here, here's T, here's P, degrees of freedom, all from the calculator. Here's alpha. And since alpha is smaller, if P is greater than alpha, your results are not significant and we fail to reject HO. we do have sufficient evidence to believe that online learning hurts the performance of students in AP statistics, okay? So let's go ahead and scoot up and look at the confidence interval, right? And hold on a second, I forgot how to move it up. I'm just going to pause for a moment. All right, guys, sorry for the pause. I'm back. In case I didn't say it, P is greater than alpha. Your results are not significant. We're going to fail to reject HO. So there's insufficient evidence to believe that online learning hurts the performance of students. Like there's really, we're not seeing any deficit in what's going on. So when we do the match pairs T intervals for means, we should trap 0. So back at the calculator, let's go back in there, and we're just going to run that. So this will be menu and 6, and I believe that'll be 6 again. And we'll do a T interval. We're going to put in data again, same thing. And the list will be the difference. And we're going to change this, all right? You may recall that a 95% confidence interval will not work for a one-sided test like we just pulled off. We need 5% on the right tail, and we need another 5% on the left tail, so it's symmetric. That's, confidence intervals are two-sided. So we're going to change that to 90% to keep things consistent, and hit OK. And there's our interval. And since this is negative and this is positive, negative here, positive here, 0 is in there. So let's go ahead and go back here. There is our interval, 90%, and here's the low end and the high end. So the usual thing is we are 90% confident that the true average difference in report card grades from in-class learning to online learning for AP Stat students falls in that interval. See the nice context? Since 0 is found in the interval, there may not be a difference at a 90% level. So your evidence points to the belief that online learning doesn't hurt student performance, right? Yeah, so it matches up to your test of significance. I didn't repeat all of those other conditions because I already have, whoops, what's supposed to happen? I already have them up here. You know, I've already listed and confirmed them, so why do it twice?